Good morning, everybody. Today we have another Codeforces round. This is round 812. I thought I'd start on this screen because someone put a good amount of artwork into this picture, and I think it looks pretty good. So if it's this guy, I don't really know how to pronounce the name. I don't really know where it ends and where it starts. Good job. I like the effort. And it's like a very pretty blog post overall, I just gotta say. Yeah. Also, kind of interesting, all of the digits here are powers of 2, so hopefully that has something to do with it. But yeah, we'll see. There will be solutions to all of the problems at the end of the video. You'll have timestamps in the description. And let's jump into it. Oh, I didn't register. Dang it. Well, oh well. I'll have some rapid fire submissions 10 minutes in, I guess. Okay. There we go. Traveling salesman problem. You're living on an infinite plane with a Cartesian coordinate system on it. In one move, you can go in any of the 4 adjacent points. Up, down, left, right. More formally, if you're standing at some point, you can go left, up, down, right. Okay. There are n boxes on the plane. The ith box has this coordinate. It's guaranteed the boxes are either on the x or y axis. You can collect a box if you and the box are at the same point. Find the minimum number of moves to collect all these boxes if you have to start and finish at 0, 0. Can you do it in any order? Okay, I'm just going to say right off the bat, this is not obvious. This is like a very hard problem A. I'm going to read problem B. That strikes me as very hard. You have an array of n integers. You can perform the following operation. Select 2 indices L and R. Decrease all of the elements in this range by 1. Let this be the minimum number of operations needed to change the array into an array of n zeros. Determine if for all permutations B of A, f of A is less than or equal to f of B. So is there a way of ordering it where this number decreases? So this one, yes. Or this one, it's not. This one, it's not. This one, it is. So does it decrease and then increase is the question. We can do that. So max, or if A at I is greater than A at max dex, then max dex equals I. So initially we'll say it works, and then we'll say like that print line, if it works, then print yes, otherwise print no. And then works and equals A at I is greater than max dex. So we want, this is too big, or greater than A at I plus 1. I equals max dex, I plus 1 less than n, I plus plus, works and equals A at I is greater than or equal to A at I plus 1. P. This is easy? You're telling me this is easy? You can go left, right, up, or down. You have to collect all the boxes. I'm telling you, this is not easy. Zero indexed array A of size n is called good. For all valid indices I, AI plus I is a perfect square. Okay. Given an integer n, find a permutation that's either good or determine no such permutation exists. Okay. Interesting. So let's think about this for a minute. We've got 0 is a square, 1's a square, 4, 9, and some other stuff, but we'll leave it at this for now. So we can get 0, 1, and then we can get things up to 4. So this is plus 0. Oh, this is now plus 0. Plus 0, and then we have 1, and then 2, 3, 4, 5, 6, 7, 8, 9. So if the length is a perfect square, if the length of the array is a perfect square, we can just do it in reverse order. What if it's not? So this will give us, yeah, we'll probably split here, right? So this would have given us, we would have 1, 2, 3, 4. Five, 6, 7, 8, 9. Yeah, I guess we want to look at the things that indices can have instead. So 0 can have 0, can have 1, 4, or 9, I guess. 1 can have 1, 3, or it can have 0. I guess we should do this a line lower. This can have 0, it can have 3, or it can have 8. This can have 2, 1, 0, 7, 6, 5, 4, 3, 2, 1, 0. I guess there is none of those. Okay, so then this is here. So we need to place 0 and 1. Where are we going to place 5? So you got to place 5 here. Or there is no 9, so you get this, right? So you place 8 here. 7, 6, 5. Yeah, so it's got to be, we need an 8 here. We need 7, 6, 5. So we don't have any of these now. So we still have 2 places for the 4. We only have 1 place for the 3 though. So 3. 1 place for the 2. Oh, that's kind of weird. Now we only have 1 place for the 0. And now we only have 1 place for a 1. And the 4 goes here. Odd. But okay. Alright, sure. So, fine, but what happens if we just go up to 7? Then what? So now, that kind of throws a wrench in everything. Yeah, this is like 8, 7, 6, 5, 4, 3, 2, 1. Which I guess works. You put 0 here. Okay, fine. So, and this is the only way of doing it. Interesting. So this, we also get 8, 7, 6, 5. Okay, there are 2 4s, but there's only 1 3. So we get this 3. There's only 1 2. So we get this 2. What now? 0. We only have the 1 0. Oh, there's no 8. So we still get 7, 6, 5. Okay, with this 3, 2, we can't place. 7, 6, 5. Okay. What about 4? We have 2 4s. We have 2 3s. We only have 1 2. This 2. Okay. Well, this has to be a 3 because nothing else can be here. This has to be a 4. And then we need a 1 here and a 0 here. So this is like 9 minus 2. It's an 8, 9, yeah, 9 minus 2. This is 8 minus 1. What about 3? So we have no 7. Can't put the 2 here. Alright, so we need to place the 6 here. Then we need the 5 needs to be here. Okay. Then we only have 1 place for the 1. So the 1 goes here. Then the 0 goes here. Okay. What about the 2? We have 1 place for a 2. Put a 2 here. Really, a 2 here. 2 plus 2 is 4. Okay, I guess it works, yeah. Alright, and then 3, 4. Six, 5, 4, 3, 2. So there is only one way of doing it. That is really wacky. Like, I haven't made any decisions this whole time. There's only one way. 7, 6, 5, 4, 3, 2, 1, 0. 6, 5, 4, 3, 2, 1, 0. Does this work forever? Really? Okay, what about 10? Eight, 9, 10. Okay, so this can be 0, and the 10 can be what's the next? 16? So we can get a lot of things with that. You can get, so it's 10 plus 6, 7, 8, 9, 10. We also have a 9 here. Oh yeah, you always take a suffix. So you take this suffix up to 6, and then you take what's less than 6, everything less than 6. 5 to 4, 4 to 1, and then 0. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, so it is always possible. There's one way to do it. Okay, so yeah, you need the, what do you start with? That took me too long to figure out. Start with the biggest. How are people doing on A, by the way? Oh, I can submit. Did I register? Register. Submit to B. Okay, man, am I just really stupid? Like, so many people have A. I don't see it. I don't see it at all. All right, we'll come back to A. Let's just get C real quick. So you start with the biggest. Square number. Or the first square number bigger than n? Wait, so what's bigger than 16? 5 squared, 25. What is the ratio between two adjacent square numbers? 1.2. That's the golden ratio. Oh, over 99 over 99. Oh, so it's about 1. Okay. So yeah, how big does this actually get? Do we want the first one? Maybe not the first one. Oh wait, maybe we do want the first one. So 9 gives you 9. Yeah. Okay, so this will be int start, will be 0. Okay, what is this? So int n equals this. All right, int start equals 0. So while start times start is less than n start plus plus. So now we have this thing. Okay. And then into place is n minus 1. I guess this is less than to place, right? You need to place 0 to 9. Ooh, is this true? Plus 1. Okay, I'm off by 1. It's a little annoying, I'm not gonna lie. Okay, let's go look at what the heck is up with this. You're living in this Cartesian, you can go in 4 directions. Oh, they're all on the axes. Dang it. Okay, alright. I see. They're all on coordinate axes? Yeah, this is important. Okay. Alright. Well, that goes from like very difficult to not that hard, but doable. Okay. Int array x's equals, well, yeah, so we need int min x, max x, min y, max y equals 0. And then for equals 0, n plus min x equals math.min min x fetch.extent. So min x, min y, max x, max y. And this needs to be max x, max y. And then sys out that print line, max x plus max y minus min x minus min y. And we should be good there. Okay. Times 2. Good. Let's get us C. 0. Oh, it is 0 indexed. Yeah, okay. So we're actually not off by 1. Alright. Did we get that, by the way? Nice. Okay, so we have this, so we just need to do it now. Okay, so less than or equal to place, then start plus plus. Now we have this. Okay, so we'll do this. Okay, so we need to keep placing this as long as we are okay. I guess, well, to place greater than or equal to 0. Int per index. This will be start times start. This is the index minus to place. If per index is greater than n, int earliest placed at will be n. It's greater than earliest placed at. Then we will say greater than or equal to, then start minus minus, and continue. Otherwise, ants at earliest, or yeah, so then ants at per index will be to place minus minus, and then earliest placed at equals math.min, earliest placed at, or per index. And then for into I in ants, out.print I plus a space, out.print line. I think we're good. Place minus minus. So start is getting really small. Okay, so I have 0, 0 or 1, 0, or 2, 1, 0 even. No, 1, 0, 4, 3, 2, 1, 0. Yeah, okay, so start is 4. Start times start minus to place. 4 minus Placing 2 at position 2. So we have 0, 1, 2. Place 2 here. Okay. Placing 1 at 0. Ah. Yeah, that's a problem. Okay. Yeah, so this is the issue. Alright, there we go. That was a mess. But we're fine. It's almost certainly right. This is an interactive problem. We have a tournament of 2N contestants. The first contestant competed with the second, alright, we got it. Second, third, and fourth contestant. Oh, first competed with second, third with fourth, and so on. After that, a winner of the first match competed with the winner of the second match. And so on, okay? The tournament ended when there was only one contestant left who was declared the winner. Such a tournament scheme is known as single elimination tournament. You don't know the results, but you want to find the winner of the tournament. In one query, you can select 2 integers A and B of 2 indices of 2 contestants. The jury will return 1 if A won more matches than B, 2 if B won more matches than A, or 0 if their number of wins were equal. Find a winner. Oh my goodness, what is this? In no more than this many queries. 1/3 times 2 to the n plus 1. In other words, 2/3 of 2 to the n. So we have n people, we can query 2/3 of them, and we need to find the winner. Well, half of the people lost immediately, right? So in one round, how many matches are there? Results are fixed and do not depend on your queries. Okay, interesting. Interesting problem. I actually really like it so far. It's quite good. Usually these tournament problems are absolute trash, but this is very clean and nice and well built, I think. So congrats to the authors. My only writing suggestion would be, and this is a little, I'm biased here, you should have bolded this part, I think. But okay, yeah, see. So we've got 0, 1, 2, 3, 4, 5, 6, 7. So in the first round, half of these people win. So how many queries do we have? And no more than rounded up of 2/3. Of 2/3? Yeah, 2/3 of 2 to the n. So what is 2/3 of 8? 6, so we get 6 queries. So how do you build a group of 4? So one of them 1 2, 1 1 1, 1 1 0, or 2 1 0. So the big numbers are rare. Yeah, it's rare to get a big number. You got a lot of zeros. Half the numbers are zeros. So we need to find the biggest number. Yeah, you've got lots of zeros. You've got some 1s. You've got a couple 2s. You got 1, 1, 3. So we want to find the 3, looking by like some comparison. But we can't even do n comparisons. So the only way to be faster is to compare pairwise elements. Oh, if they're equal, we don't care. So if you compare like 0 and 2, and they're equal, you kill both. Worst case, you kill one of them. What about 1 and 3? Ah, if they're not equal, then you kill 3. Look at this. All right, interesting. So we compare 0 and 2. Yeah, look at this. All right. So we have 0, 1, 2, 3. Okay, so if we do 0, 2, and they're equal, then kill both. Right? Because then they're either both 1s or both 0s. And then we do... Yeah. And then if 0 is greater, then we kill 2 and 1. Can we do that? We can now, anyway. Yeah, okay. And what if 1 is greater? Or 2 is greater, I mean. 2 is greater, then we kill 0 and 3. So, okay, what do we wind up with? Well, maybe this isn't too useful, but after n over 2 queries, we have n over 2 remaining. Is it n over 2 or n over 4? Every query you kill 2 things. Yeah, so we have 6 queries, right? We end up with, we take 4 queries. Oh wait, yeah, all right, it's n over 4 queries even. Over 4 queries, we have n over 2 remaining. Okay, and now we have a tournament with n over 2 things. So we have n over 2. Well, so what's our final runtime, right? Worst case, we do this. We have n over 4 plus n over 2 minus 1. After n over 4 queries, we have n over 2 remaining. This would take n over 2 plus 1. So this would be 0.75 n, but we need 0.66 n. I think on average, what's the chance two things are equal? Oh, well, in one query, there's a 50% chance you kill 2. Maybe it's more than that, though. So now, yeah, what happens after I do one round of this? If I kill both, if they're equal and I kill both, what if they're both 1? Ah, that's kind of a problem, isn't it? Okay, yeah, does this extrapolate? So yeah, I did 0 versus 2. My goal is to get rid of all of the zeros. Well, I don't need all the zeros. I just need to not get rid of the winner, right? That's my only restriction. So I compared these two. If they're equal, well, they could both be 1s. So then I would get rid of all the 1s. So it would be all 0. So I could let 0, 0 through. I could let 1, 1 through. I could let 2, 1, 2, 0. Yeah, I guess that's it. 0, 0, 0, 1, 2, 1, 2, 0. Right? Wait, what if I just never compare two things that are equal? Anytime they're equal, I can stop, right? That's the idea? Maybe that's what I'm getting here. Ah, okay, yeah. 4, 1, 2, 3, 4, 5, 6, 7. Alright, so I did 0 versus 2. What if I did 0 versus 4? And 2 versus 6? So 0 and 4 are the same. Kill both? You might end up with a 50% success rate though, which is not good enough. So you need like 2 kills per thing. Lots of solves in D, huh? Guess so. All right. Sounds somewhat hackable though, I'm not gonna lie. All right, can I just continue using this? So if they're equal, kill both. That's always fair. So this always works. All right. What if one is greater than the other? I can kill the other. This is okay. What about killing one? This is kind of sketchy. Yeah, because you could have 2-0 versus, you could have 2-1 versus 2-0. You do 1 versus 0. This is not okay. So this is the issue, isn't it? Well, no, this is the issue. All right, so this diagonal stays constant. If I just read this problem, the diagonal stays constant. Then I think the column things are in stays the same too, right? Yeah, so if you're here, you go here, but it always stays kind of the same. So 1 3 1 1 3 2 2. Oh, this is interesting. And then 1 1 3 2. Yeah, this one not sorted is interesting. I guess because it's tied to this one, huh? You can choose to swap these two if you want. So wait, the first row. Let's look at the input. T. So the first row is the most important. Right, so we want to maximize this here. I guess it's just the upper diagonal is all that matters, right? Because the lower diagonal's forced? Not quite. So this one is determined by this, which means what we do with this is fixed. Oh, but we could maybe switch this. Yeah, he is interesting. Okay, I guess we'll go back to this tournament one. So we can kill 2 people with 1 query. Have you guys ever thought about the saying 2 birds with 1 stone? Like, can you imagine actually doing that? That would be like insanely impressive. Like, throw a rock and it hits 2 birds. Killing 1 bird with 1 stone is like really. Like, can you imagine throwing a rock, it hits a bird dies? I mean, just yikes. You gotta have some good aim. 1 bird with 2 stones, even. It's like still. Ugh. Maybe they're talking like a boulder. Knock a boulder off a mountain and starts an avalanche. Technically, you got 2 birds in that. There's only 1 stone. I guess I'm David, right? It's David and Goliath. I should be thinking slingshot. I wonder if you hit a bird with a stone, how much does it ricochet? Like, would you aim to go through the bird? Or do you try and bounce it off one, hit the other? Because like surely it's not like the bird isn't like fixed, right? It's not like a wall where you can easily predict it depends on the mass of the bird, and also I guess the angle you hit the bird, right? If you hit the bird, it's like pool. It's like a Yeah, 2 birds with 1 stone. That's a tough thing to do. That's a tough thing to do. Maybe it's like pool. You got the birds lined up, right? You hit the first bird, boom, boom. It just like hits the second one. So you killed 1 bird with 1 stone, and then you killed another bird with the first bird. Anyway. Let's go back to solving problems. What do you say? Let's eliminate 2 people with 1 query. In 2 queries, we can get the greatest of 4. There you go. There you go. In 2 queries, you eliminate 3 people. And then you repeat. Alright, so how many queries does this take? So for 2, it takes 1. For 4, it takes 2. For 8, it takes 2 plus 2 plus 1. 5. Which I think is good enough. Yeah, I think we should be fine. Because this is less than 2/3. Yeah, I think we're good. All right, I think it's asymptotically fine. Okay. So, yeah. All right. Cool. How does this work? So we're gonna have int t, 1 test case. It's gonna be a bit confusing, okay? And int n equals this. And then we'll have static void solve. And this will have an array, list, integer, alive. Okay, so initially we have 1 to 2 to the n, right? So 4 int I equals 1, I is less than or equal to 2 to the n, plus plus. Array list integer alive, new array list. We'll say alive.add I. Then we'll say solve alive. Okay. Cool. So if alive.size equals 2, static query int a and b. Static winner. Oh, I guess we want the winner. So this out question mark a plus b, and then we'll have static scanner fs equals to scanner system.in. Don't need this, don't need this. fs.extent. So then what do we print here? If it's one if A wins, 2 or 0 if the number of wins are equal. Okay. So then return new int array of -1 A B at next. Alright, so then int winner equals winner of alive.get0 and alive.get1. And then sys out, exclamation point, winner. Okay, and then we start the next one, I imagine. Okay, so otherwise, then return. Otherwise, we need to split this into groups of 4. So 4 int start equals 0, start is less than alive.size, start plus equals 4. All powers of 2 that are bigger than 2 are multiples of 4. Is that true? 8 is a multiple of 4. Yeah, it is. Okay. That's very obvious. If you just look at them in binary, the answer is of course, which is why we should be using numbers, a power of 10, where 10 is a power of 2. 10 should be a power of 2. We should do base 16, base 8 if you really want, but base 16 is better. Okay. Because then that would be an obvious fact. We would all know that. Okay. So here we have int A equals this, B equals this, nope. Int A equals alive.get start plus 0, B, C, D. And then 1, 2, 3. Okay. So int A, C, winner equals winner of A and C. And then we'll have B, D winner. Or no, we don't need that. Okay, so if AC winner equals -1, then solve this. What do we do here? So this will be, this winner is -1. Then next alive.add winner of, oh, what if it's -1? Okay, int next winner, well, it won't be. Yeah, it won't be. If they tie, someone's got to win. So then next alive.add the winner of B, D. Otherwise, if it's not, else if AC winner equals A, otherwise it equals C. All right, so then okay. Otherwise, then next alive.add winner of A. This is A and C, so A versus D. Otherwise, we need the winner of B versus C. Okay. Then we keep doing it, and then we're done. We're done. Okay. Oh wait, can there be 1? 2 to the 1. Yeah, that's fine. All right, let's try it. One test case. 2 to the 3rd. 1 versus 3. 3 wins. 2 versus 3. 3 wins. 5 versus 7. We'll say it's a tie. 6 versus 8. The 8 wins. 3 versus 6. it's a tie. -1? Oh, yeah, okay, it's fine. I think this is actually right. It's very hard to test, but it's not right, for real. I wonder why. Do we use too many queries? Oh, what if this as equals 1? One, 3. Say 1 wins that. 1, 4. Let's say the 4 wins that. Well, that's a thing. Okay. 1, 2, 1, 3. The 1 wins that. 1, 4. The 4 wins that. So this was almost certainly a runtime error. Or could it be a wrong answer? Hello? TLE? What? How do I TLE? For real? How? How though? It's order n. Is that an output size thing? 2 to the 17. Nope. 2 to the 17. Do we need a print writer? And then we flush it? Maybe we just need to do this in C++. So both of these cases return instantly. And then the only other case, equals 0, less than this, plus plus, these would crash. And this is this, very quick. First line is the number of test cases. Oh, only up to 2 to the 14. Well, no, the output's still 2 to the 17. Dang, do we need this in C++? Is that the solution? Alright. This is my wrong drive. GitHub. The Java files? It is Java files, that's ironic. In my Java files folder, I have well, we're just gonna hope it works, huh? Alright, let's convert. Okay, so what do we need? This part. In T, sorry, CNT, and we can do a for loop, that's fine. Okay, and then we have some stuff. Int n, cn, vector of int alive equals, we'll make this n, fill it size n, I think, and then no, we can just do this alive, yep, and then alive dot push back I, and then solve live. Okay, so then we need void solve. So take in a vector int alive. Okay. If alive dot size equals 1, we do this. Cout exclamation point and then alive 0, and then indel. Okay. Alive that size is 2. Winner will be this, and then we'll see out the winner, indel. And then what if it's not 2? Vector int next alive. So this will be this, and then that. This will be the winner of these two. If the winner is this, then this will be this dot push back. It's all next to life. Okay. So now we just need winner. Int winner. Int A. Okay. So Cout question mark A space B and L, and then int next cn next equals 0, return -1. If next equals 1, return A, return B. Okay. This should be at winner alive at 0. Dang it. Okay. So one test case, let's do the 2. 1 versus 3, let's say that's a tie. 2 versus 4, let's say 4 wins. All right. Submit in C++ 14. It's really gonna TLE? No. Dang it! Setters, fix your Java. It's so un-Java friendly. It's ridiculous. Ridiculous. Okay. Yeah, it's very unfriendly to Java. Okay. Ooh, so this is kind of tricky. How are people doing? Giga Buffoon, love to see it. Anderson, my boy. Whoa. Whoa, Andy. Oh my goodness, Andy. Andy, you are in 2nd place. Let's go. Good job, sir. Good job. Andy really did quite poorly last round. But now he's earning it all back. Let's go. Okay. Very well. Very well done. Okay, let's look at this cross-swapping. We can get this. Looks like we just got, according to the lights, we just got the interactive one. So that was like Java is just annoying. Yeah, not much you can do, I guess, other than not use Java, I suppose. We're given a square matrix A of size n by n, whose elements are integers. We will denote the element on the intersection of the ith row and jth column as aij. Okay, in each operation, you can perform an integer k. Yeah, we've done this. Okay, so let's take a look at what happens here. So like the first decision we need to make, yeah, so really we pick like a, oh, does order matter? If we do this, then this, then this, than this. AB, AB. What happens? Okay, let's say dot A, B dot C, D, E, F. Okay. So we flip the first one, and then we get A, C, B, D. And then we flip, I guess let's put a dot here. And then we flip the second one here, and then we get A, E, B, F. All right, then we flip the first one again, and now we get A, D, B, C. And now we flip the second one, and we get A, B, what's this? Uh-oh. Yeah. A, B, C, D, E, F is what we started with. Yeah, does this have any other place it could ever even possibly be than this? I don't think so, but it's not, you can't just always sort them because these two can switch spots, so. So wait, so what am I thinking? I'm thinking like, is it possible to swap two elements? The answer is no. Because if it was, then yeah, then clearly that sample wouldn't be right. So what I'm trying here just doesn't work. You can't just swap two elements, okay. Well, of these two, we need this one to be there, right? So there are two ways of doing it. We can do this, or we can do this. And then later on, we can swap both of these for free, if we want. So if these two aren't equal, they're not. I guess let's just choose this top one. So then we'll get 1, 3, 2, and 3, 1, 2. Okay. So now we're worried about these two. We should indeed swap them. So we do this. Yeah. One. Two, or all threes. Okay, this or this, they're the same, so move on. This one. It's the same. This one, yeah, so I guess it's just these. Alright, so this. Can we swap this with this? No. This with this? No. And this with this. So these two you could swap, but doing so affects one of these, or one of these. So let's say we know whether or not we're going to take this. Then either, it doesn't matter if we mess these up, or it does. Yeah, so this is probably pretty easy. So, okay, so the idea is brute force whether or not we flip. Oh, first question, does order matter? No. For each element, all that matters is the parity of the number of times it was flipped. Right? Because it just swaps between two places. The answer is just no. Okay. So brute force the number of times, or brute force whether or not we flip the top left. And then all others are decided. Okay, then, yeah, I guess just like iterate through column by column on top left. Okay. All right, we can get this very easy. Okay, so how do you do this? So int n equals this, and then we get the grid. Repeat array says n. Oh, we need the get min. Okay. Int double array a, int double array b. Okay. So 4 int I equals 0, I is less than a dot length, I plus plus. 4 int j equals 0, j is less than a dot length, j plus plus. A at ij is not equal to b at ij. And do one thing, otherwise do the other. So if it never happens, then return a. If it does happen, if a at I j is less than b at I j, return a, otherwise return b. Okay, so then 4 into times equals 0 times less than 2. Okay. Cool. Yeah, so we have A and then the clone of it. We might as well just not do this. Yeah, I guess we'll just have ugly code and then deal with it later if we need to. So Boolean array flipped equals new Boolean array n. So we're going to start with not flipping. Okay. So then for int I equals 1 less than n plus plus, we want to see, are there any positions that would rather flip than not? Okay, so then we're going to need a get, static int get. So this would be int double array a. Then we need Boolean array flipped, and then we need int I and j. Okay, so int times flipped equals flipped equals 0, I guess. If flipped at I, then it's one more than that. And then same thing if we flipped index j. Okay, and then we need to say that we should read it or not. So if times flipped mod 2 equals 0, then return a at I j. Otherwise return a at j I. And then static int, well, yeah, let me just do this. Okay, so and for int j equals 0, j is less than I, j plus plus. So we'll go down the column. We want to see, does this care? So int me will be get a flipped ij. And the int other will be get a flipped ji. It doesn't even matter if we flip the top one, right? You flip the top one and everything else? No, it doesn't matter. That is a different grid. Okay. Wait a minute. Does this work? Okay. Okay, so yeah, we do have some issues here. Like the grid can contain duplicates, so maybe the solution doesn't quite work. The issue is that like whether or not the first thing is flipped might matter. Okay, so maybe let's look at this in a better way. So we have 1,000 nodes. We have 1,000 nodes. We have a bunch of edges, either different or same. And then we want to maximize, or we want to we want to lexicographically maximize the number of edges we satisfy. Yeah, okay, so this is like a decent amount easier. Okay. We don't need this. I think we can probably code this in a bit. Okay, so we need to get, this is actually a very cool problem. Very cool problem. So we'll have this and then not this, yeah. Right, so disjoint, so we'll have A, not A, B, so disjoint set dj, new disjoint set, this will be size n times 2. Okay, and then for int I equals 0, I is less than n, I plus, for int j equals 0, j is less than I, j plus. A at I j equals A at j I, then continue. Otherwise, if A at I j equals A at j I, less than, if it's less than, then we want same. Otherwise, we want opposite. Okay, and then afterwards, we'll go through again. So here, well, yeah, we need to print it still. How much time do we have left? 18 minutes? I still think we can do it in 18 minutes. Okay, so if these two are the same, what does that mean? That means if this is flipped, this isn't flipped. Yes, they're both flipped or neither flipped, right? Static boolean can join int I int j disjoint set dj, and then can separate. Okay, so if dj dot find I equals dj dot find I left shift 1, j left shift 1 plus 1, return false. Yeah, because this would join something to the opposite of something else. If this is already the opposite, then it's impossible. If I is the same as not j, it's impossible. Otherwise, I is the same. If I equals j. Yeah. Otherwise, return true. And then this is kind of the opposite. So this is just, can you separate two things? Well, if I equals j, if they're the same component, then no. Otherwise, you can. Okay. All right. So what if they're the same? So if can join ij dj, then dj dot union I left shift 1, j left shift 1, and then union this plus 1, and j left shift 1 plus 1. Okay. What about if they're opposite? Then can separate. That's probably not how you spell separate, but make fun of me in the comments. If you can separate I and j, then we do j plus 1. Otherwise, we do just j, or and just j. Okay. All right. So, yeah. So then we'll say for equals 0 less than n plus plus if dj dot find I left shift 1 is equal to dj dot find I left shift 1 plus 1, then row null. And otherwise, we need to print the answer. Okay, so then for equals 0 less than n plus plus, j equals 0 less than n j plus plus, less than I mean. Okay. So let's say ants. So ants at I equals a at I. And then what else? This will be if ants at ij, or if a at ij equals a at ji, then ants at ij equals ants at ji equals a at ij. Otherwise, yeah, so otherwise we have tried to connect them if we want to, or tried to disconnect them if we don't want to. So otherwise they're either connected or disconnected, right? Yeah. Okay, so painted or cut, I guess here. So what does this mean? So if dj.find I left shift 1 is equal to dj.find j left shift 1, then ants at ij equals a at ij, and then same thing with ji. Otherwise, they're reversed. Okay, and then after this, we say for int I equals 0 less than n plus dot print line for int j equals 0, j is less than n, j plus plus. Dot print, say instead I j to space. So here, if it's less than this, union these two. So we're getting this straight up wrong, right? Yeah. Interesting. Okay. I know it's not how you spell separate. It's just how I spell separate. All right, separating 0, 1, 0. Oh yeah, we only have 0, 1, and 2. Okay. Separating 0 and 1. We shouldn't be separating them, we should be joining them. Oh. Oh. Joining 0 and 1. Okay, looks right. Did Andy solve set? Okay. Wait, where am I? Oh, I got D, right? Good, okay. Just TLE. How did we do? Probably pretty well. Yeah. Okay. So we can take a look at F, but it's just there's no time. My Orslers, we can optimize this problem from S cubed to T to the cube, whatever. Not sure what this is talking about. My Orslers. That's really funny. I really like that. Orslers. I've never heard Orslers before. That's good. Orslers. There we go. Alright, got you. Nice. Top 100. Solid, solid. Yeah, we're not quite as fast as geothermal, but Andy's doing a good job. How is Andy doing? Xylonox is Andy. He was my ICPC teammate. We went to Russia together, and yeah, I competed with him in World Finals. Great guy. He's super young. He was like 12 or something when he went to college. Maybe 13. I think 12. Maybe he was a bit older. Maybe he was like 14 or something. But he was very young. Very young. Yeah, I guess he probably wasn't 12. Anyway, when I competed, he was older than that, but he still wasn't 18. I think he had like just learned to drive when he was going to World Finals, which is like surprisingly not that rare for people who are like crazy good at competitive programming. Like, they're disproportionately unlicensed. Like, they don't have their driver's license. Just, I guess, because they spend all their time coding, and it's just not important to them. If you've got a computer who really needs, like, yeah, still second place. That's quite good. And then this looks like an alt. No, maybe not. Well, could be legit. Probably not their first account. Maybe it is. It is a bit suspicious. I don't know. Could be legit. Could be legit. Yeah, that's pretty good though. Nice job, Andy. Nice job. Okay. Yeah, so I guess talk about solutions. Solution time. Okay, problem A. Yes. Most important part of this problem is this line right here. So all of these points are either on the x-axis or on the y-axis. Yeah, so basically they give you these complicated things, but you'll always want to go right, left, up, down, left, right, down, up. Right, and that's always equivalently good. You can do these complicated things, but you can always just like make a cross, right? And you're done. So it's just the max x times 2, the max y times minus 2, the min x times minus 2, the max y times 2, and the min y times minus 2. And then also add just like the 0.00 in there as well, and then you're good. Yeah, so it's actually very easy. The code looks like this. So yeah, you just take the min and max of the x's and y's, and then it's just this. I use this a bunch of this contest. Left shift 1 is the same as times 2, and it also has like lower priority, so you don't have to do it, but you can do this here times 2. That might make more sense to you. So yeah, that's problem A. Hopefully it makes sense why you can just go like this. Obviously there isn't a better way of doing it. Okay. In general, if you're allowed to travel along not this direction, this can be a really hard problem. If the points can be anywhere, you can travel in any direction. This is like a very, very difficult problem. But if you're only allowed to travel in like up and down directions, you can do better. And you can use this thing called Mohs algorithm to guarantee a bound on the solution. And I think you can always do it at most 2 times the worst case with this type of constraint. And you definitely can do that with the general case, using some minimum spanning tree stuff. But yeah, anyway, here you go. This is the solution to A. They get harder if you're looking for it. Variants of A can get very hard. All right, optimal reduction. So here you have some array of n integers. Yeah, I didn't solve A for a while because I'm like, I didn't read the fact they were only on the axes. I thought they could be anywhere. And it's like, oh man, this is a tough problem. But it turns out it's not. Only on the axes makes it very easy. Okay, problem B, optimal reduction. So in this problem, you have an array, and you want to turn the array into all zeros. And to do that, you're going to pick a range of the array and subtract 1 from each element in that range. So you can imagine if your array represents like heights over time, you take a range and you move that all down by 1, right? So I guess I'll draw a quick picture here. So maybe it's like you've got one thing that's 1 tall, you've got one thing that's 2 tall here, you've got one thing that's 3 tall, you've got a thing that's 1 tall, and then something that's like 2 tall, and then 1 tall, for instance. So maybe you've got an array like this. So what one operation is you take these 3, and then you move like this entire chunk here. You move this chunk down by 1. So you get space XX, and then this after moving them all down. Okay, so that's the idea. That's what one operation is. And the question is, well, first of all, like the question is like, if we shuffled these heights, right? If we shuffled these in some other order, could we make it take less minimum turns or fewer minimum turns? So in this case, the answer is yes. We could take this column here and move this to the end. So at the moment, this takes 1 turn for this, and then 1 turn for this, 1 turn for this, 1 turn for this. So 4 turns in total. But if we moved this to the end, so we move this over, and we get this, now we can do it 3 turns. So really, what the question is asking, the solution part of it is the array something that is increasing and then decreasing, right? Does it form like a mountain? And it can be, you can have tides, right? So you can have something like this, right? It can be increasing to a max, then go down, and then kind of like level off, and then keep going down and stuff. But is it something that like doesn't have a V, never has a dip? So to calculate that, what you can do is just find the max index, or the index of the max. I call it the max dex. This is maybe doesn't make sense, but if you have the index of the min, then that's the min dex, like min index. So you've got the max dex too, if you want. Kind of a fun word that I like using. But yeah, you find the max dex, and then you just see if everything before then is like increasing, and then everything after that is decreasing or going straight. And that's the idea. That's what this does. And equals is just the same as like works equals works and this. So you get the idea. So it has to work for the entire part before you, and then also this step has to be an increase. That's what you're looking for. All right, that's problem B. We'll give you problem C here. Problem C is interesting, I guess. So yeah, I don't know how someone invented the problem, but it's pretty cool. The idea is you have some array, and it's a 0 indexed array. So the indices start at 0. It's like 0, 1, 2, 3, 4, 5. Usually we start them at 1, 2, 3, 4, 5 in like problem statements, but here it's not. So anyway, we have a 0 indexed array, and we want to make a permutation of the numbers 0 through n minus 1, so that for every position, the position plus the value at that position is equal to a perfect square. So square numbers are like 0, 1, 4, 9, right? 4 because it's 2 times 2, 9 because it's 3 times 3, 16 because it's 4 times 4. So we want each of these to be a square number. So as an example, if we go to, if we look at this array, right? This has all the numbers 0 to 8, and in position 0, we have 0 plus, this is index 0, right? So 0 plus 0 is a square number. Then we have index 1. So 8 plus 1, this is 9, which is a perfect square. And we have 2. So 7 plus 2, this is also 9, also a perfect square. 6 plus 3, also 9. So yeah, all of these are 9. And the question is it possible? And if so, do it. Now, as you can see, there are no samples for which it is impossible, which is mighty suspicious. And it turns out it is always possible. And I think it also turns out, in fact, there's only one way of doing it, I suspect, from what I worked on paper. And yeah, I don't really have a proof for this, but I suspect if you looked at it long enough, you could figure out why. But the idea is we're going to do this thing where we look at, for each square number, what elements can we write there to add up to it for each position? So I'll explain what this looks like here. So so let's look at the square number 9, for instance. So for 9, if we want to write something at position 8, we have to write a 1. There's nothing else we can write at position 8 for it to equal 9. Because obviously, right, 1 plus 8 is 9, that's it. And yeah, for position 5, you can write a 4, and it can add up to 9. So this is like the 9 column. And then this here is the 4 column. And this is the 1 column, and this is the 0 column. So yeah, in this case, 0 plus 4 is equal to 4. All right, so you can like do some stuff with this, and you can like do some math, and like you can be like, all right, so there's only one 8. We have to put an 8 somewhere, so we got to put an 8 here. There's only one 7. We have to put the 7 here. There's only one 6. We'll put the 6 here. There's only one 5, so we have to put the 5 here, and so on. But here's the easiest way of looking at it. We can just fill out the biggest numbers from 8 all the way to the end. And when we do this, we're going to use a suffix of the array. We'll also use a suffix of these numbers of the same length. And this will recursively get us to a smaller version of the problem, right? So what do I mean by that? Well, here we're going to use 8, 7, 6, 5, 4, 3, 2, 1. We'll use this suffix, and we'll place it in these indices. So when we do that, we've used the last 8 numbers and also the last 8 positions. And that's the same as we can do this part of the problem, and then what we have left is solving the problem with just a 0 and one position 0, right? And then we can put the thing in position 0, if that makes sense. So we'll put 8, 7, 6, 8, 7, 6, 5, 4, 3, 2, 4, 3, 2, 1. And then we're left with the stuff before this, which is just the 0. We're good there. Okay, let's do another example. This one here. So here, the biggest thing we could place, the biggest total we can get is also 9. So we'll place 6, 5, 4, 3, 2, or 6, 5, 4, 3. We'll place them here. So we place 6, 5, 4, 3. All right, now what we're left with is we have to place the numbers 2, 1, and 0, and we have to do them in these positions. So we'll do that, and we'll place a 2 at the end, because with the 2, we can do 2 plus 2 equals 4. So place the 2, because 4 is the next thing we can get. Place the 2, and now we're left with this group. So we have to place 0 and 1, and we need it to have in position 0 and 1 when we actually do that. So first, we place 6, 5, 4, 3. Handles these ones, and then we did these all add up to 9. Right, so we do this all at once. Now we're looking for this 4. Now we look for 4. So to look for 4, we can get 2 plus 2. So we place 2 all the way until we hit the end of the array. Okay, we're actually already at the end of the array, so we're done there. Now we're looking for 1. So what things can we do to 1? Well, we can do 1 plus 0 and 0 plus 1. We get this. Now we're done. So this is like the solution there. Okay, that's the visual solution. This just like does that. Yeah, I'm not going to really explain how this works because it's not particularly useful. You actually don't need this either, but yeah, this is like the implementation of that. And the idea is you find the biggest square number that you can use, and you use as much of that as you can, and that'll use a suffix of the array and also a suffix of the numbers. And then you can continue going on with a smaller square number. I may have said power of 2 earlier, I meant square number. So you use a smaller square number and an earlier part in the array, and just keep filling them in like that. Okay, hopefully that made sense. Gonna move on here. Problem D, tournament countdown. I almost read it as tournament clowntown. Yeah, so this is actually a really cool problem. I really enjoyed this one. It took me a while, but okay, I really enjoyed it, but the authors need to like give us more time, please, or something. Like cut down on this. 2 to the 17 and an interactive problem is too much. Too much. We need 2 to the 17 queries. That is too much for Java. So take it a step back, please. But anyway, yeah, really cool problem. How do you do it? Well, all right, so what is the problem first? So you have a bunch of people like this. They play in one of these tournaments, and the number of people is a power of 2. And 2 people play, one of them wins and moves on, the other person is eliminated. So the single elimination bracket. For each person, the computer knows how many wins they have in this bracket. And you want to find who is the winner. Now, obviously what you could do is just say, okay, who has more wins between person 1 and 2? That person is the current winner, then of, like, let's say that's 1. Who has more wins between 1 and 3? Well, it's 1. Who has more wins between 1 and 4? It's 4. So then we have 4. Who has more wins between 4 and 5? It's still 4, right? So we can do this in n-1 queries. We can find the answer. That's pretty easy. But they want us to do it with this bound here, which is less than that. It is 1/3 times 2 to the n-1. Now, this is sure, but an easier way of looking at this is 2/3 times 2 to the n, right? This is equal to 2/3 times 2 to the n. So what this means is for each person, or for each person, they should take 2/3 of a query on average to get rid of. And then they round this up at the end to make it a little bit easier for us. But in the long run, when there are a lot of people, we need each person to take 2/3 of a query to get rid of them, which is kind of weird, and I'll explain where that comes from in just a minute. So yeah, what you might think of doing is like, okay, you've got, let me try to not spoil all of this here. Yeah, you've got these people here, right? So let's consider like the first 2 people. If these play each other, one of them's going to win, one of them's going to lose. But you can't just query these 2, because you'll eliminate one of the people, but the other person, you haven't learned anything about them, right? So this isn't a very useful query. Instead, we can query the 0 and the 2. And this gives us more information. Here's why. Let's say, like, this person won, let's say the tournament only had 4 people, right? So let's say this person won 0, this person won 1, this person won 0, and this person won 2. If we query both of these and they're the same, what that tells us is that neither of these people are the winner of these 4. They both lost. Because you're not going to have a tie at 1. You won't have 2 people in this group that both have won 1 time. You'll have 2 people that won 0 times, 1 person that won 1 time, and 1 person that won 2 or more times. So we want to find the person who won 2 or more times, and we're going to do that in 2 queries. The first query will be query these first 2 people, and if we get the same thing, then we query these 2, and the winner of those will be the real winner. Okay? So you try these 2, and then you try these 2 if it fails. What if one of them wins? So there are a couple ways that can happen. Let's say we have one of these. Let's say we query this one here and this one here. So this guy wins. So we don't know whether this is like a 1 or a 2. We just know it's bigger than this one. So obviously this one is not the winner, right? We can get rid of him. But we don't know much about this, and we don't know much about this here, right? We just know this guy's not the winner. So we can actually determine something about this because we know these 2 people played each other. Person 1, person 2, they faced each other. And if this guy beat him, that means he has at least 1 win. So the win has to be against this player 2. So player 2 also can't be the winner. So importantly here, we've just eliminated 2 people with 1 query, and one of the people we eliminated, we didn't even ask him any questions. So this is like very useful information based on the structure of the tree. Okay, so if somebody wins, we can eliminate 2 people, and if they tie, we can eliminate both of them. Now, this is like very useful. The problem here is that we can't keep doing this. So, yeah, we can eliminate 2 people with 1 query, but this only is true when we're guaranteed the smallest number everybody has is 0, right? If, like, this guy won, we can only eliminate this guy because we know it has to be less than him. But now that we've done this, right, we could leave this with, okay, this guy has a score of 1 and this guy has a score of 2. So we don't, like, right, if the scores can be anything, if we don't have any structure on the scores, then we can only do this fancy thing 1 time, and it's not enough. So we have to do better. Okay, so how do we do better? Well, we now ask these two a query, and we find the real winner. So when we do that, okay, so yeah, we'll ask these two the query, and we'll see, okay, this guy wins, so we'll kill this guy. Okay, so we kill these two in the first query, this guy in the second query. So in total, we kill 3 people with 2 queries. On average, it takes 2/3 of a query to kill a person. Now, why do we do this instead of like stop early with the better thing? Here's the reason. When we've killed 3 people with 2 queries in every group of 4, we now know everyone who had 0 wins and 1 win is gone. So this is the same as a tournament with a fourth as many people. That wasn't true after we did just 1 query. Because after we do just 1 query, sure, you can remove half the people in a fourth of the queries, right? So it's a very efficient step. But after you do that, you can have people with 0 wins, 1 wins, or 2 wins. And that loses your freedom in future steps to make these decisions. So that's why you have to take the 2 steps at once. That's the idea. Okay, I'll go through the code, and this will be a brief explanation of like how it works again as a recap. So we're going to go through this in groups of 4. There are 2 base cases. One base case is if there's only 1 person left, he wins. If there are 2 people left, we see which one's better, they win. This will only ever happen once, right? So it's not very efficient, but it only happens once, so it's fine. This is the efficient part that we have to be careful with. So we're going to have a bunch of people, and we're going to have a fourth as many people on the next step. We know n's a power of 2, and all powers of 2 that are bigger than 2, so 4 and above, are all multiples of 4. Because in binary, all powers of 2 are like 1 and a bunch of zeros, and they all have at least 2 zeros if they're 4, right? So that's proof. Okay. Sorry about my air conditioning in advance. It makes bad audio. Okay, so yeah, so how does this work? So we have the 4 people. We have A and C fight, and if the winner is no one, if they both lose, then we have B and D fight. Okay, so if they tie, that means they're either like both 2, or they're both 0, or they're both 4, or something like that. They both have that many wins. So that means neither of them won this group of 4, because that winner has more wins than everybody else. Okay, and then what if one of them wins? Well, if A wins, we want A to fight D, because we know A is better than C. We know A is better than B, because A isn't the worst, and B must be the worst if it lost to A. And we don't know whether, we know A is better than C, but C could have been a 0, right? So we need A to fight D as well. So we have A and D fight, and that person stays alive. Otherwise, we have B and C fight, and that person stays alive. Because we know C is better than A, we know C is also better than D, so C might be better than B, so they should fight. Okay. Yeah, that's the idea. All right. The problem is this TLEs, for whatever reason, probably because we're doing a lot of print lines and a lot of nextins, right? So I don't have fast input output, so it's slow. But you can have fast input output because you have to flush every time, right? So there's not really much getting around it. So I wrote this code in C++, and it's literally the exact same thing, and it passes. Which means the time limit was too tight. Anyway, yeah, that's problem D. Maybe you can blame me for using Java, but there's no way that wasn't the intended solution. I don't really know if that problem was possible in Java. It's like it feels like the meme of the dog who gives you the weird like down his nose glance, if you know what I'm talking about. Anyway, okay. Last one, problem E, cross swapping. There's also problem F, I just don't know how to do it. I didn't really read it. Okay, problem E, how do you do it? Cross swapping. So yeah, in this problem you have a grid, and you're allowed to do this operation here. So just like this picture is the best way of explaining it. You take a column and a row, and you like switch them, right? So the column becomes the row becomes a column. They'll share one space, but it'll be the same, so obviously it stays the same. So this is like what happens. And the question is, if you do this operation as many or as few times as you want, what is the lexicographically smallest array you can end up with? So in particular, you want this element to be as small as possible, Among all ways of doing that, you want this element to be as small as possible. Among all ways of doing that, you want this element, and so on, in row major order. So yeah, that's the problem. All right, before you start solving this problem, you have to make a couple of observations. The first one is that the diagonals here never change, right? There's no way of changing anything along the diagonal. That's the first one. The next observation is that the number of places that this position can move to, right? Or let's look at this 3. We have a 3 here. So where could this 3 move? Well, it could move to this spot here. So the 3 and the 9 could switch spots. But that's the only other place this 3 could ever be. You could also move the 3 by querying this 1 here, but still it would switch places with the 9. So any operation that affects the 3, it'll make it switch places with the 9, and any operation that doesn't affect the 3, well, the 3 won't move. So there are only 2 places this 3 can be. And that's true for every number, right? The 3 and the 9 switch places, so they're kind of like linked together. Every other number is like linked together, or it's linked with itself. So yeah, it's a less complicated problem than you would think. You can't just like do anything you want, right? You can't just like shuffle the entire array. So that's something to be interested in. Also, you can look at the samples and you can see, in this case, you have a right answer that doesn't just swap every pair to the lower position, right? So what I was trying to do initially is like come up with some Rubik's Cube way of solving things where it's like flip this, flip this, flip this, flip this, right? But if you look at this, clearly it's that they don't exist. There's no way of doing some flips to swap 2 things and keep everything else the same. It's just not possible. Because if it was, then you could leave the rest of this the same. You could get a lexicographically better answer by flipping this 3 and this 2. So that's like an interesting thing to consider, which I thought might be helpful to explain. So, okay, you've got that observation. Last observation, which I think is very important, is that the order that you do the operations in doesn't matter. That's pretty clear from what we've previously explained, but like to formalize why, every time something affects you, you switch places. And every time something affects you, it'll also affect the place you'll switch to. So like the 3 and the 9, if you ever hit the 3, you'll also hit the 9, right? Because they switch places, obviously. So all that matters is if at the end we have how many times did we use each thing in this diagonal. If we know how many times we used each of them, we can just say, okay, you did 5 operations that affected the 3, so it went 1, 2, 3, 4, 5. It switched from the top to the bottom. 5 is odd, so it switched, right? If you did 4 operations, it'd be down, up, stayed at the top. 4 is even, so it stays there. So all that matters is the parity of the number of times that you flip each element. Okay, now let's talk about the solution. So we're going to turn this problem from a problem on a grid to a problem on a graph, which is a pretty common thing to do, but in this case, it's completely different. The nodes aren't just like all of these positions. The nodes are just the diagonals. So we have 4 nodes here. We have 1 node for the 1, 1 node for the 6, 1 for the 7, 1 for the 2. And then we have a bunch of like constraints that we would like to have here. So in particular, we want the number of times we picked 7 and the number of times we picked 1. We want their parity to be the same because we don't want to flip the 3 and the 9. So 1 and 7 we want to be in the same group. And then let's look at something else. Okay, so let's look at this 2 here. So this 2 and this 2, both of them are the same. So we don't care. So we're not going to have any restriction on 1 and 6 directly, right? All right, let's look at this 8 and the 4. Or sorry, let's look at this 4 and the 5 here. So the 4 and the 5, we want to keep it the same. So we would like the 1 and the 2 here to stay in the same groups, right? We would want either both of them to be changed or neither of them to be changed. Okay, and then I guess let's look at one more. So we have the 7 and the 8. So this affects the 6 and the 7, right? And we also don't want these changed. So we want the 6 and the 7 to stay where they are. So we want these to be in the same group. We either want them both positive or both negative. Both positive, we either want both of them to be flipped an odd number of times or both to be flipped an even number of times. Okay. An example of when you might want things flipped different numbers of times is the 6 and the 3, right? So 6 comes lexicographically before 3. So we want the 7 and the 2 to be different. Now, it's possible we can't satisfy all of these restrictions, but we want to satisfy each one greedily if we can. So, like, we don't want to satisfy the most number of these restrictions. We want to satisfy the biggest prefix of them, right? The biggest prefix, and then after that, the biggest prefix, and so on, right? So, like the lexicographically maximal set. So we want to satisfy the 2 edge, then we want to satisfy the 3 edge, and then this 4 edge, and then this 7 edge, and then the 8 edge, and then the 6 edge. And eventually, we have maybe, like, potentially a lot more edges than we do nodes. So a lot of these we'll just have to ignore, or they'll already be forced to be true or something like that. So yeah, I guess we have to be a little careful there. So that's the idea behind what's happening. Yeah, I'll show you the code here. So to implement this, I use a disjoint set, and I've got like copies of each node. So one will be, is this changed? And one will be, is it not changed? And two things will be connected if I want them both to be either like both true or both false. So for instance, if I want the 1, if the 1 is changed, I also want the 6 to be changed, then I'll connect the normal 1 to the normal 6, and then the flipped 1 to the flipped 6. And that would be like if this number here, this top 2, if you imagine this was like a 1 and this was a 2. Okay, I don't want to flip these two. So I connect normal 1 to normal 6, flipped 1 to flip 6. If I do want them to be changed, then I'll connect the normal 1 to the flipped 6, and then the flipped 1 to the normal 6. Yeah, so that's the idea. Okay, so we've got this disjoint set, and then we have A, and then we have like the flipped version of A, right? And then B and flipped version of B. So we'll go through all of the elements that aren't on the main diagonal, and if they're equal, it doesn't pose any concerns to us, but if they're not, then this will be a condition that we'll try and satisfy in some way. If it's in the right order, if they're in the correct order, then I try and keep it the same. Otherwise, I try and make it opposite. So what are these can join and can separate? Well, if this thing is already connected to the opposite of the other thing, then it can't be connected to the same of the other thing, right? If this and the other thing are already forced to be opposites, they can't be forced to be the same. Otherwise, I force them to be the same. And then for everything else, these things have to be the same. So like if we make 1 and 2 are opposites, and then 1 and 3 are the same, that means 1 and 3 will be one thing, and then 3 and 2 will be opposites. And using a disjoint set, we can combine all these together. And then I also have the can separate, which is just like if these two are already forced to be the same, then, well, we can't separate them because they're forced to be the same. So yeah, my first time going through this, I process all of these restrictions. And then this you don't actually need, but this is just like me sanity checking that I did all this right. If anything is in the same group as its opposite, obviously you can't have both like something can't be both flipped and not flipped at the same time. It can only be one of them. So yeah, that's the idea. Okay. Yes. Next. Yeah. Finally, I just go through and find out for each edge whether or not it's satisfied. So obviously, if it's on the diagonal, then it's easy. And if we don't care about this, it's also easy. Here's the other thing. So it turns out, I think this is true, but actually I know it's true. We have already tried to force everything that we have a say in to be in a certain position. Yeah, so like we've already. I'll stop explaining this as if I know exactly what I'm talking about, because really I don't. But we've already forced things to be in the position they're going to be in, right? So they will be. And we can just say, like, is the condition satisfied? And if it is, then like if they're in the same group, then we'll keep them the same. Otherwise, if they're in opposite groups, we'll flip it across the diagonal. Yeah, and then I print it. I know it was a bit hand wavy. I hope that helped a little bit. Oops. The observations in the beginning are the important part. So, and then from there you can use a disjoint set to solve it. Okay, any other parts of the code that I haven't shown? I think that's it. Here's the disjoint set. If you don't have disjoint set, you can copy it here. That's the idea. Okay. Yeah, that's all. And there's also problem F, but I don't know how to do that. So you'll have to struggle through that on your own, I guess. All right, thank you all for watching. I hope you enjoyed, and congratulations to Andy for doing a fantastic job in this contest, and congratulations to Tourist for winning Google Code Jam yesterday. That was very impressive. The man did it again, and he is best programmer of our time, probably best programmer of all time. But yeah, absolute unit right there. We'll see how he does in Hacker Cup, and yeah, there you go. If you are interested, you can sign up for Facebook Hacker Cup now. It's facebook.com/coding competitions, I believe. Here you go. It's called Meta Hacker Cup now. I should know. I'm pretty sure I renamed that button. And then you can sign up for the Meta Hacker Cup right now. Would highly recommend it. It starts on my birthday on August 26th. And yeah, good luck, have fun in that. Hope you enjoyed the Codeforces contest today. Goodbye.